Welcome to Brain Vision.
Okay, in this problem, we're given two different scenarios where we have a weight hanging off of some cords, and you're asked to calculate the tension in each one of the cords here. So let's draw out our situation. We have our first diagram here, and we have our weight hanging off, and we have C, A, and B. And the A chord is at a 30-degree angle, and the B chord here is at a 45-degree angle to the ceiling. So I'm going to mark points 1 and 2 here, and we're going to draw force body diagrams for each point. So the force body diagram for 1 is pretty simple. You just have chord C, the tension in that pointed upwards, and you'd have the weight of our object pointed downwards. In our second force body diagram, we have a few different forces pointing in different directions. So we have A pointed off like so, B directed upwards, and now C is pointed directly below. And just so we have throw in our reference frame here. So I might break down A and B here into the components of C, just so we stay within the XY reference frame that I've established. So we see that C will just stay the same. And if we break the B down into components, the vertical component of the tension due to chord B will be B sine of 45 degrees. And the horizontal component then is B cosine of 45 degrees. And we're going to do the same thing with chord A. You see the vertical component is going to be A times the sine of 30 degrees. And the horizontal component is A times the cosine of 30 degrees. Okay, so we have our force body diagrams. We have 3 unknowns in our tensions in the 3 different chords, and let's see, we're going to have 3 equations we're going to set up here. So from free body diagram number 1, we just have the tension due to C minus the weight is equal to 0, assuming no acceleration. So we see that C is just equal to W. In our second part, let's do the horizontal components first. We have B times the cosine of 45 degrees minus A cosine of 30 degrees equals 0. And here we have B sine of 45 degrees plus A sine of 30 degrees minus C is equal to 0. So first things first, I see I can substitute W in for C here and move it over to the other side. And that will give me this equation here. And then now I have a system of equation with 2 unknowns and 2 equations. Here and here. So I want to eliminate one of my unknowns here and then solve for the other. So we can use our knowledge of trig to say that cosine of 45 degrees is equal to sine of 45 degrees. So if we just subtract these two equations from each other, the first terms in each one will cancel each other out. So that would leave us with negative a cosine of 30 degrees plus sine of 30 degrees is equal to negative w. So those negative signs on either side cancel out, and in the end you get that a is equal to w over cosine of 30 degrees plus the sine of 30 degrees. And when you plug in the numbers for cosine of 30 and sine of 30 degrees, you'd get that a is equal to 0.732 w. Now let's move over here to now solve for b. So from this equation, we can get b in terms of a. So it will just be a times the cosine of 30 degrees times the cosine of 45 degrees. And when you plug in the appropriate values for a and b, I get that this is equal to 0.897 W. So in the end, we solved for the tensions in all the chords. We found C, A in terms of W, and B here. So with that, we are ready to move on to the next part. So let's look at scenario B here. You're given something that's hanging in the corner, the ceiling, and we have one cord coming down from the ceiling, one coming from the wall, and then at the intersection point of the two cords, we have one cord hanging down. And again, we have some weight hanging off of this. And our angles have changed a little bit here. We have a 60-degree angle at the bottom and a 45-degree angle on top. So just like before, I'm going to make a force body diagram for 2 points we have here. We have C, W, and again, can't forget my reference frame here. Always a good thing to label, so that's 1. And then 2, we're going to have another free body diagram where we have the forces pointing in all different directions. So we need to break down some of them into their components so that we can write out Newton's second law equations. So when I break A down into the components, the vertical component will be A times cosine of 60 degrees here. And so go ahead and label that. And the horizontal component will be A times the sine of 60. And the vertical component of B will be B cosine 45 degrees. And the vertical component will be equal to B times the cosine or sine of 45 degrees. But those are synonymous anyways. So just like last time when I set up my Newton's second law equation, so I have C minus W equals 0. So like in the previous part, we have just C is equal to W. Then we have B sine of 45 degrees minus a cosine of 60 minus C, and I'm just going to insert in W now, since we already know that, equals 0. So B sine 45 degrees minus a cosine of 60 degrees is equal to W. Then in another equation, we have B cosine of 45 degrees is the positive part, and the negative part of that is a sine of 60 degrees, and that would all be equal to 0. So again, we see that we have two terms that are equivalent, since sine and cosine of 45 degrees are equivalent. So if I subtract these from each other, we would get A, and I'm just going to keep this coefficient positive for now. And you'll see I'll leave the negative that you get here inside our parentheses. So isolating A here, we get that it is equal to this expression. And when plugging in the proper values for the sine and cosine of 60 degrees, I find that A is equal to 2.73 W. And just like before, we can use one of our equations here, the B cosine 45 degrees minus A sine of 60 degrees equals 0 to put define B in terms of A. So we have B is A times 60 degrees cosine of 45 degrees. And so this is going to increase the value of A so that B is a larger tension force and is equal to 3.35 W. So we have now once again solved for the tension and the three chords, kind of crossed out the answer there in this figure.